Hello everyone, my name is Kooshan Hashemifard and I am doing my PhD here in University of Alicante with Paco. And my topic is context recognition for the application of visual privacy. A little bit about the motivation. As we all know, the demographic changes is happening and the number of older adults in Europe is gonna raise a lot. So it can be a damage to care personnel and facilities. One of the possible solution and promising solution is AAL technologies, among which video-based technologies are very important because they are the most direct way to record an event and they can provide rich information. But on the other hand, they have the problem of be very easy to interpret by unauthorized viewers. So in my research project, context recognition for the application of visual privacy, I am trying to find a visualization method to understand what is happening at the same time preserve the privacy. So make this balance between privacy and intelligibility in the video. And as Sid mentioned, previous work in our lab introduced level-based visualization and privacy by context. And my objective is to make this process automatic and make this happening automatically, this changing in the visualization methods according to the context. For this task, we need to define the context. We need to define the context by some variables. We need to model the context. So among the variables that we can add to the context, it can be activity, it can be incident that is happening in the context, appearance of the person, the observer who is watching, the place. In my PhD, I am tackling the first three, the activity that is happening, the incident, and the appearance. So the research question can be defined like this. Can we automatically estimate the context that may affect visualization, preference? Can we estimate relative activities and can we estimate relative events? Also, can we estimate the degree of nudity? And how can we integrate all of them to have the privacy by context, visualization, and system? So first, the first thing that I tackled was the appearance. During the appearance need is very important in video-based technology because there are serious concerns about the people being recorded nude or not partially nude in the video, which they may not like to, especially if these videos they are recorded in the private places. And we need to find a way to estimate the degree of nudity of the people. So about the background of this work, usually they are not directly tackle this problem. So most of the literature are both either is in obscene image classification, such as detecting pornographic content, or in the garment detection. The obscene image classification is very naive approach because it's not level-based visual classification. It doesn't give you the level-based and also fail to generalize the problem. Also, it can be very subjective what they can consider as covered or nude. But the garment detection is with the goal of detecting the different wearables and clothing. And they have very big data set thanks to the fashion industry, which trying to detect the clothing on the videos or in the image to do the market analysis. For our task, since we don't have the direct data set that it is related to our work. What I decided is to use the data set from this garment data set and make it reverse. For example, here we have an image from the data set from the garment data sets. By using body segmentation, hair segmentation, and using the annotation of the clothing that the person have, and also some filtering these results by adding and subtracting from each other, it is possible to reach to the skin exposure map of the data of the corresponding image. And for example, here the study has been done because around 300 of images annotated, segmented and annotated automatically. So with this different filtering, we try to increase the maximum or the most accurate skin mask to be used as our ground truth. Regarding the architecture, I use the encoder-decoder architecture for using as a segmentation thing with two additional modules. One is the body attention mechanism, which try to make the network focus on the area of the body, and the second one is the skin attention mechanism, which use this assumption that some areas, such as for example face or hand, would be consist of a skin, and try to validate that through the whole body to see which are the similarities. So in this way, it helps the network. But as we said, since our data sets are generated automatically, so for training, I use the weakly supervised system, so also the ground truth of the network gets corrected during the further epochs during the network. So some noise of the data set will be handled. Here are some results of the proposed network. You can see in the top rows some networks that are, or some state of the art at that time that they were working on this task, and also the proposed network. And the proposed network, the base network also, and each of the study has been done on each of the different attention module, how the effect is on the results, and also the integrated method. But having the skin exposure map is not considered as a nudity directly, because we need to have some more intuition about this. So this is the framework that I proposed with the help of my colleague to have the levels-based visualization, which we have a skin exposure, we have the body part segmentation, and with the user preference regarding of each body part and the level of nudity on that body part, system can provide a level-based visualization. And this research also has been done for the preferences of the people and these nudity levels that they considered as their preferences in most of the cases, from the completely covered body to the full body exposure. Second context variable that I tackled was incident detection, which it was during my 3 months stay in Maynooth University. During my exchange, I tried to work on the fall detection. And since the fall detection is kind of solved problem, I tackled it in a way of an object detection, and I put the focus on most to make it more efficient. So it's an end-to-end object detection with 2 classes of fallen or upright persons or individuals. And there are data sets of the fallen of the older adults that has been used for training and fine-tuning this data. But for making more efficient knowledge distillation methods has been used, because lots of CNN architecture, they use lots of computational power, which is not really which is not very efficient for this task. So using the knowledge distillation, we use the bigger network to train, and after that, with using the smaller network to learn the features that are produced in the mid-level of that network. So the network will be much more efficient regarding the computational power. Also, we recorded there the real-world data set with the cameras that they were using in the Maynooth University. This Loxanus cameras, and we captured with them to have our own data set to see how is it going to work on this. And here are some results of the different models, and the last row is the one that one of the small models which is being trained using the large model. So we can see that the improvement between the last row and the last row, one row before it, it is because of this knowledge distillation that we get from the large model. And the third part and the last part of the work is the activity recognition. For this task, I used the Toyota Smart Home dataset because the task was to detect the activities from daily living, and especially for the older adults, which this dataset really fits the task. The dataset has 35 class of activities and ISO data modalities such as RGB, depth, skeleton, which could be quite helpful. Regarding the activity recognition in regarding the deep learning method in human activity recognition, we have some steps because we need to use the information in a spatial in each frame, what is happening in each frame, and also we need to consider what is happening between the frame. For spatial information, utilizing CNNs are very common approach that we are doing, or they are doing in the deep learning. And for temporal information, also there are lots of methods that can be used. Such as using RNN networks or using higher dimension CNN. So this also can be useful to encode the temporal information between the frames or during the time axis. Also, the transformer help me, as they work quite well in natural language processing. Also, they started to being used in this vision, computer vision, and they can also provide lots of good information. They are also capable of doing these two tasks at the same time with different methods, actually. So in my approach, it has a different, the approach that I use for activity recognition, it has different blocks. One of them is to choosing my backbone network just to do the feature extraction, which among the lots of networks that are there, I3D network works quite well. Also, there are slow fast network and other networks for getting these features or getting some embeddings or encoding the video into feature domain. Another thing is, as we said, in this data set, we have the pose information. So the pose information can be quite helpful because in RGB, it can be, it's not very robust to change in appearance or change in a person, but the pose data that we have of the skeleton of the body can be quite robust to these changes. And the relationship between the joints of the body or the skeleton during different activities can be also view invariant because you will do the same, and if you normalize that poses, it can reach to the same thing. And also there are some methods to do this processing of these. There are some methods to processing this skeleton data as a graph. So pose data as a graph can be used with GCNs or graph convolutional networks, which I am using that also in the network that I want to use. Another thing is, since we know the activities are doing in the home environment, we know that some objects definitely gonna be helpful during the activity, during the detection of the activity. And for this task, and especially we know that it is the house object, so I trained the YOLO model or object detector with these 8 classes of the objects, and we classified them as one class. For example, from the kitchen furniture to living room furniture or to electronic furniture. So we have these 8 different classes. Putting all them together, we can use this feature extractor and using with the cross attention between the different object masks with each of these classes, we can have some encoding of the spatial dimension, and also using the GCN and the network that process the pose of the body, it can be helpful for having the information or encoding the information during the time series or during the time. And here we can see some models that also there's some benchmark of that were always used on this data set, the modalities that they are using RGB or skeleton or pose data, and also the different things, for example, the cross-subject test or cross-view test that they have. We can see that lots of them, they can vary in some aspects, they are good, but they can drop the accuracy in another metric. In the one that I am proposing in cross-subject, it works quite well. In cross-view, it's not beating any of them, but it has the closer, it's in the closer range, so it's not very lower in one aspect, in one metric comparing to another one. And we can see even, I also did a study for without using this pose data, and the accuracy definitely gets lower. And the last thing that we are working on, as the seed introduced this data set, the activity labels of this data set also are created. I chose 29 labels of the videos that are usable, which became at the end 850 videos with 29 labels of classes with RGB and pose data. So this data set we are right now, I am training lots of these models that you saw in the previous slide on this data set to see how they're going to work on this kind of distorted top view to see how much is their accuracy of each of these models on that. So bringing all them together with appearance, incident, and activity, we can now look to the privacy by context system, which using the privacy filters which are previously developed in our lab. And I implement them in this Jetson device. We had our first demo of the privacy by context system, which we can see, for example, if we choose this visualization for a normal thing, when something happens, some incident happens, and the person falls, the visualization can be changed to another thing and can be detected automatically and can be changed. So we are maybe a step closer to privacy by context system. And thank you for your attention.
Thank you. Thanks. Yeah, are there questions? Context. To start with the question, when you presented the list of the YOLO's different versions, the version of YOLO, are there? I mean, is that, would you say, the only way you could compare these images in the are there other data sets available or other approaches to say how good your approach is?
So, which data set you mean that they are trained on?
You use YOLOs in different versions, but is that like the golden standard, or would you say that there are more options to?
No, actually I did also lots of other object detector because, for example, lots of more because, but the YOLO version, they were working much better. So at the end I decided to do this method for the knowledge distillation through the YOLO networks because they were performing much better.
Okay.
In a paper that actually I published on it, I also brought the result of the other methods and said why I am choosing the YOLO.
Comments or no? No, if not, then thank you very much again.
Thank you.
Okay, thanks. And the third one is Hassan. Okay. The next one is Hassan, and he's online, as Baki just said. And let's see if he's ready to present. I hope so.
Hello.
Yep.
Okay.
That sounds good.
One moment. Okay, you can share. You are sharing your display. So now put it in presentation mode. Okay, now.
Right. So Hassan, he is a researcher at the Trinity College in Dublin, and he will talk about improving home-based care robots' capabilities using natural language interface. So please, Hassan, go ahead.
Hello. Thanks, everyone. I will talk about improving home-based care robotics for capabilities using large language interface. So this is an overview of what I will talk about. I will give some background why we will use the robotics for this case for all adults and what is the aim and objective of this work. And we will talk about large language models as is the main research like for robotics focusing, and what we propose like architecture to use that to control the robot, and conclude like that. So the background, in the EU, the old age dependency will be increased from 29.6% in 2016 to more than 51% in 2070, which is more than half of population will be. And this aging demand, in this aging society, the demand for healthcare, it will be increased, and then, like as more than half the population will be old age dependent, so it will be like needing more people to work. So there is many research indicate that like okay, robotics could be help in that in that case, and could help support in aging in place. So here, for example, I use a case scenario. Cara from Ireland, she's 87 years old. She has lung cancer. She has visual impairment, and she like robots. For example, she like gardening. She want a robot to help her to carry the tools to garden, and also like for example, she want a robot to remind her about her medicine and fetch this medicine to her. So for that, we're starting like looking at what is the robots available for healthcare for all the adults in general. We can see some of them for transferring, some of them like for helping movement, some of them for social and interaction. And like we evaluate these robots, like a set of robots that we identify from research related to the activity daily livings and social needs, user needs. Here we can see like this set of robots and like how is the activity daily livings, and you can see like the table is sparse. But at the end, we need to focus in something, and based on the visual and what we see in the table, we decided to focus about indoor object transferring. So, which is needing a communication for that. Like we need to having as Cara, for example, in the scenario, she wants something natural interaction as a human interact. So the aim of this objective, this work, to enhance communication and interaction capabilities between the robot and the human, and also we need to build on that what the robot can do and what cannot do, with the environment of the robot, but also what is available in this environment and what is not available in this environment. And based on that, also we started, I will explain later, but to do different things, but recently with the development of large language models, we're starting to investigate using large language models. So just here background also about grounding large language model with visual scene. So for example, if you interact with the robot, sometimes there is a gesture, sometimes there is what the robot need to understand what inside the scene. So for example, nowadays we can see vision language models and large language models. So yeah, so we started before vision and large language models started. Honestly, my work started. I started with vision and language navigation. Vision and language navigation, for example, is give very detailed instruction for the robot, which is later we discovered, okay, this is nice research, but it's not really realistic. For example, go to the stair, then turn right, then pass the desk, and then go to the table, for example. And then the robot need to connect what the user give and the details instruction to the what is seeing in this environment. This is nice for research, as I said, but as a human, we don't interact in this way. We interact in abstract. Bring me a water. Bring me this. It's very abstract. We don't go to the direction, the kitchen, turn right, do this. It's not always this case. Other things for also for interaction with the robot, what available before, it was a set of the instruction, couple of instruction, and that's it. But with large language models, people starting to investigate how to use it for robotics. Some of them for perception, decision making, controls, interaction, and starting using large language models or vision language, with images, not just a text. So here I just want to mention what is the benefit and what is the limitation of large language models that are available now for robotics. Large language models basically started by training in a lot of text data, and now with images data. So it could be asking I spelled my name, can you help me? So for example, some examples of different large language models suggesting something try using vacuum cleaner or other, find a cleaner, or what do you mean by that? But this is a limitation. Here, for example, in this environment, there is no vacuum cleaner. As we said, it's trained with a set of text. So a significant weakness of large language models that lack of real world experience. So it doesn't know exactly what the robot capabilities, what inside this environment that the user interacting with the robot about it. So in the research, we can see there is after large language models, other companies starting to investigate. For example, Google, Secan. So let me. So as we said, like this work, honestly, as I started vision and language navigation, but like as we said, it's not realistic. So like this work, it triggered, okay, let's move to using large language models for robotics. This work is good, but it's like when reading the details, what it's happening in the work, there is like a lot of things, limitation. For example, the equipped robot, like there is a dictionary of skills that the robot can do. And this is for this environment, is like this dictionary for this environment, for this robot. So if there is a changing in the environment or the changing in different robots, it cannot be like doing these actions that we see. And also it assumes many things that the robot knows where is the location of the object. It's also like doesn't considering planning for the hierarchical environment, especially AI. So this is like, just let me explain why like we need special AI for robotics. For robots as a human, like okay, we can understand, go to the kitchen, these things. But for robots, it needs a different level of understanding the environment. It's starting by understanding where I am. So this is the localization level. But it's need also the robot to move around without like hitting obstacles, without avoid obstacles or hitting objects. So it needs to around where is the object surrounded by me. So this is the mapping. So mapping and localization, the robot can moving inside this environment. But the robot like, okay, seeing as object, obstacle, not an obstacle, this is what it see in the environment. But to make the robot understand more like what is inside this environment, it needs like semantic knowledge about this environment. So what is this object? Is it a table? Is it chair? Is it what it is? And then like more than that, it's needs like, okay, how this related to each other, like this laptop, for example, on the table, this chair next to the fridge or something like that. So it need to know how the environment is organized. This is the, like how to explain for the robot the environment. So this is like, as I said, like large language models give very good answers, but it's sometimes unrelated to the robot or the environment. So here we are like our work to analyze this using large language model for two things, by conditioning it to what inside this environment and what is the robot capable to do. So this is like our focus in this area, like large language model conditioned with visual scene and robot capabilities. So it could be then able to adapt to changes in the environment or different robot embodiment. So for that we need like prompt engineering for robotics. Why robot prompt engineering? It's like, as we said, large language models in general, two things, transformer and human feedback reinforcement learning. So it's basically, it's work about like a prediction, what is next. Like if we give it a window of like text and what is the next word probability, so to predict what that. So it's like, there is a context of window. So it's provided what is the task about it, what is the user instruction, instructed. So give me a water, something like that, not details what is inside the environment. Then we feed it like what is inside the environment, what this robot can do. And then this output like something that the robot can understand, structured command for the robot that can understand it. So just here to mention, like in large language models, to improve the responses, there is two ways. There is prompting and there is fine tuning. Prompting, it doesn't changing the parameters of large language models. It's just like there is a windows and it's moving this window. So if when we ask large language model something, it's a provide answer, and this answer including now in the windows. So if we want, like if we don't like the answer, we can ask it, like give it more details. We can give something so it's to improve the answer. So this is, but the windows still will shift. Now it's like becoming large window with the improvement of capabilities of large language models. Other things, it could be fine tuning. This fine tuning is changing the parameters of large language models. For example, even like now, some of them like using large language model for specific application, for medicine, or something like, if we want to use it for navigation, it might be affecting other capabilities in an unpredictable way. So it doesn't like, okay, if it's improved in this way, still it gives better results as others. So yeah. So for that, like we talk about the prompt engineering, like why we need it. So here, for example, we are talking with the ChatGPT, like you are a guide robot for domestic environment, and you can do these actions, navigate inside the room, for example. There is this sofa table in this room, and there is a person you can interact with. So for example here, bring me a coffee. In this case, like how can do that? So here, just like as we are discussing how to design like our method. So we can start ready the position, located the coffee cup, calculate the distance, plan the back to the table, navigate to the table, stop at the table. Then here we can see like extended your arm, grip the coffee. But because here we don't provide what the robot can do. So it's expecting the robot that has an arm. So like if we improve it and we are like adding, you have arm and like, there is, you don't have an arm, you have a tray and there is a person you can interact with. So here we can say like, let's go plan to the table, navigate to the table, then notify, for example, this person, his name Ali, and then request Ali to place the coffee on the tray. So here, like we can say like, okay, there is interaction, so improve like, capabilities, starting like to understand what is inside the environment. There is some work started by that, like, okay, to connect what is the user want with what can robot implement. So, but it's very basic level without connecting, this is what is missing, we adding to this scene description and robot action description. So this is what we propose as architecture for that. We getting here our focus work now in simulation. We're getting the information from the simulation and we provide it to the large language models as a JSON file. And then like what is the robot capabilities also, and what is the user instruction, like what we want, what it want, and some description might be like helpful to give information about the environment. This is passed to like prompt construction system, which is injected to the large language models. It's give instruction subtask for the robot that the robot can understand. For example, navigate to the environment, which is different things, how to avoid object, these things the robot can do, and then like it's fed it to the simulator and what is to update, like what is moved object, what is available, and something like that. So here, for example, controlling the robot using a ChatGPT, here for rotating, for moving forward. So yeah, here the basic level it was before, like injecting what inside the environment. So yeah, and then like we having navigating to go. For example, we want to go to next room for the computer that's available in the next room. So here we can see that in the rabbits for what it's see through the sensors and how it's navigate to the environment. Here we can see the robot going to the PC that it's need to go to it. So what is the next? Like now almost the architecture implemented. So now we want to evaluate in different things. To evaluate if we have different robot capabilities, like when there is no arm, so then like it's need to interact with the user. And we just need to notice like we are interacting in the spatial AI, like not all the scene always all the time observable, sometimes not observable, and partially observable, let's say. And there is also, if the robot having an arm, okay, it doesn't need to ask maybe the user if it can be a picket. And other things we need to focus our work to study it. Like there is some issues that large language models in general having hallucination. For example, it give unwanted answers or fake answers, something like not related to the question or what is inside the environment. This is we need to study it, and what is in the memory, like because the updating what inside the environment, we need to focus about that and the safety issue. And okay, to conclude, like robots hold the promise to enhance activity, daily living, or medical needs. Large language models, it shows like it has benefit and having semantic knowledge about the world. So using this could help to enhance the communication, the expected impact that support all adults to better aging in a place. Thanks for listening.
Thank you very much, Hassan. Thank you. Are there questions or comments? Hassan, maybe I missed that part in the beginning. Which robot are you using and which large language model are you referring to? Maybe I missed that, sorry.
The robot I'm using, it's Carter now. Biggest one, Carter from NVIDIA Carter. But also I will include also the BAL robot as it has manipulator to do the different task. This is as the robot. The other question, I'm sorry. The ChatGPT now, I'm using ChatGPT for 0.40, that's the decent one, but I started by ChatGPT 3.5. So this ChatGPT 4.0, it's using images also. It's good for, but it's used image, not like, here for robotics, the problem like we often navigate to site environment, not just like one image, it's observe everything in this scenario.
So just one question. Some people mean that the language models are getting better and better and prompt engineering gets less important in the future. How do you see that problem, or how do you see that in the future?
It will be improved, but we cannot say like it will not be prompt engineering, because like this is a natural way of interaction as a human. Even like we sometimes someone asks us something, we need to clarify these things. So without prompting at all, it will generate something might be good but not reasonable or not related to the environment or the robots. So as here I just mentioned, like okay, there is prompting or fine tuning. What is the prompting? It's because there is a context. What this is like, to inject the context, we need the prompt.
All right, there's one question.
So you're saying that you're using pre-trained models, right? So they have some general knowledge, which is quite huge. I mean, it depends on the data they train on. But then how you will deal with the hallucinations problem? Because probably you need some kind of verification of what the model understood. Because it can misguide the robot, right?
Yes, exactly. That we want to study it intensively, honestly, because like already large language models without robotics suffering from it. Because even like hallucination with robotics, it might be more related safety issue. It will be later. So if there is hallucination, it might be dangerous. So for that, like we are trying to condition it with vision and robotics capabilities to give something like try to not give general answers, something that will hallucinate it, but like it will be hallucination, and that we want to study honestly, the rest of the work.
Because you cannot, if you're using like ChatGPT or any other commercially available model, you cannot fine tune it, so you can just prompt it. But then if you're really careful with the prompts, it can still hallucinate. So.
Yeah, like for example, the Llama 3, for example, or other things can be like retrained, but we can't train it again. But here, as we said, like sometimes, like even from this paper, like it's investigate like fine tuning, and sometimes in some application, it's like when you retrain it, for example, we train it again for medical application. It could be like improve the performance, but as we said, like performance in other tasks could be unpredictable change. So yeah, in general, fine tuning sometimes useful, but not always. Like if it's for just a specific application, it will be very useful.
Okay, thank you.
And in robotics, in special environment, we don't have like enough data too much, like
Thank you, Hassan. And one final question, maybe.
Right, thanks Hassan, very interesting. You talked about testing for different robot embodiments. Now, when you talk about testing, are you talking about testing the functionality, or are you talking about testing the acceptability to the end users? And I ask that particularly because of the configuration of some robots in an anthropomorphic form, which can be regarded as very patronizing to what is a large number of older residents. And their responses to the robots might have something to do with the design and the anthropomorphism as opposed to the functionality.
Honestly, we are focused about functionality because just like we want to see how the large language model convert what is like bringing me a cup of coffee or bring me the medicine, and how it's converted to based on the robot functionality. So because like for that we started even with NVIDIA Carter, honestly, because like about safety issue, because sometimes if the robot has a manipulator, it could be holding a knife and do something dangerous or something like that. So you need to focus more like about something without manipulator, it's almost not dangerous, but still like we need to compare functionality of different robots.
All right, so thank you.